In this lesson, we'll discuss the base of a number system. We'll start with the familiar decimal or base 10 number system and go from there. To start with, a definition. When we say the base of a number system, we mean how many symbols are used to represent any given number. And for this lesson, we'll consider bases B on the list 2, 3, 4, and so on. So start with decimal, which is also called base 10. Here we have the digits 0 through 9 that we use to represent any given number. So that's a total of 10 symbols. And you can write numbers like 137. And each location of these digits tells you a place value. So to start with the 7 here, the 7 is in what we call the ones place. The 3 is in the tens place. And this 1 is in the hundreds. And of course, this corresponds to powers of 10. The ones is 10 to the power of 0, which is equal to 1. The tens place is 10 to the power of 1, which is equal to 10. And the hundreds place is 10 to the power of 2, which is equal to 100. So here we're using a base to express a given number. Now, what if you were to switch the base of a number system? Like, what if you considered, let's say, base 5? What does that mean? This means we're only using 5 symbols to represent any given number of things. And those symbols will be the first 5 that appear on this list, which is 0 through 4. So here in a base 5 number system, we are using the digits 0, 1, 2, 3, and 4 to represent every single number. So an example of a number that is in base 5 might be something like 2, 3, 1. Here I'm only using these digits to represent a number. But now the place values are different. This is still the ones place, but this is no longer the tens, and this is no longer the hundreds. In fact, you can use the base to figure out the place value. Here, this is your 5 to the 0 place, which is still ones. But here, if we follow this pattern, we just increase the exponent by 1 every time that we go this way. So this place value will be not 10 to the first, but 5 to the first, or the 5's place. And this 2, this is going to be 5 squared, or the 25's place. So as long as you don't use a number that is bigger than the symbol 4, then we're okay with expressing a number in base 5. Now, some confusion can happen if you have different bases that you're using at the same time, because how do I know this is really base 5, and how do I know that this is really base 10? And what you can do is you can write a subscript after the number to represent the base. So in this case, I can put 231 with a subscript of 5, and that means we're talking about base 5. Base 10 or decimal is so common that typically we don't write a subscript after it, but it's okay to do that. You can also say that 137 here is base 10 just by putting the subscript 10 after it. I think I'll write down one other base, and let's look at base 2. What does this mean? It means we're only using 2 symbols to represent any given number, and that's going to be a 0 and a 1, and that's it. This base system is very common in computer programming. In fact, this is referred to as binary. So any number that you write in base 2 can only have the digits 0 and 1. So here's an example of a base 2 number, 1, 0, 0, 1. And for emphasis, I'll put a subscript of 2 after it to say we're talking about base 2, not base 5, not base 10. And the place values will use this common convention in constructing the number. Here, this place value will be 2 to the power of 0, which is the ones place. This place value is going to be 2 to the first, which is the 2's. This is going to be 2 to the power of 2, which is the 4's place. And this over here is going to be 2 to the power of 3, which is the 8's. So here again, we're using the base to represent every single place value. This is how we express numbers in different bases. Let's actually try counting in different bases to see how it compares to counting in base 10. In example 1, let's compare counting in base 10, which we're familiar with, to counting in base 5 and base 2, which is probably less common. So for counting in base 10, you would start with the ones place. I guess you could start with the digit 0 to say we have nothing, and then you can count using the digits that we have right up until you get to 9, at which point, okay, you have to stop. In the ones place, there are no other digits to use, but that just means we have to move over to the tens place, the next place value over. So what we do is we go back to the very first 0, so we put a 0 here, but then we put a 1 over in the tens place, and then we just continue with this process. You do 1, 1, 1, 2, 1, 3, 1, 4, and so on. So that's base 10. We're very familiar with that. But what about if you count in, let's say, base 5? And again, you're only using the symbols 0, 1, 2, 3, and 4. What does it mean to count in this base? You still start with 0, and then go 1, 2, 3, and 4. But here you have to stop. You can't say 5, 6, 7, 8, 9, 10, and so on. What we do is, when you get to the last digit in your base number system, you drop this back down to 0. And then you carry a 1 over the next symbol in the next row, which is the 5's place instead of the 10's place. And then you'd keep counting. You go, all right, now we have 1, 1, 1, 2, 1, 3, 1, 4. Okay, here again, we got to 4. This is where we have to stop in base 5. This drops down to a 1. We carry a 1 over, and that changes the 1 to a 2. And you continue counting from there. So the idea is the same. We're just using fewer digits than in base 10. If you compare this to, let's say, base 2, again, here only using the digits 0 and 1 to represent every single number, I guess this would be the most extreme case where you would start with 0, then you put 1, and you've arrived at your last digit. This means you have to drop back down to a 0 and carry a 1 over. Okay, well, the next thing you'd have to write down would have to be a 1 and a 1. Now, after this has to drop back down to a 0, and you carry a 1 over, but you can't call this 2, which means you carry another 1 over. So the next value would be 1, 0, 0. And you'd continue by going 1, 0, 1. If you add 1 to this, it'll carry a 1 over here, dropping this down to a 0. So you get 1, 1, 0, 1, 1, then 1, and you'd have 1, 0, 0, 0. The idea is the same, but when you lower the base, we just have fewer symbols to work with. One last thing I'd like to point out in this example is for base 10, base 5, and base 2, you could write a subscript of 10 and 5 and 2 after all these numerals just to distinguish the different bases. I think I'll do that for one number in each list that I'll choose at random. And I think that number will be, let's say, 7. So here is 7, and the base on this is 10. This is 7 base 10. What does that compare to in these two lists if you start at 0 and then count 1, 2 until you get to 7? So here it's going to be 0, 1, 2, 3, 4, 5, 6, 7. This is the 7th one on the list in base 5, 1, 2. So here if I highlight that one, this 1, 2, which is in base 5, this symbol here, 1, 2, base 5, is equivalent to what we would say 7 in base 10. Does something similar happen over here on this list in base 2? Let's see. Here's 0, 1, 2, 3, 4, 5, 6. Here's 7. So I'll highlight that one. So this right here, which is in base 2, is equivalent to 1, 2, base 5, or 7 base 10. You can convert back and forth between any number that appears in a given base. So here, if you have 7 base 10, that's equivalent to writing 1, 2, base 5. Or if you're in base 2, it's equivalent to writing 1, 1, and 1. What we'll look at next is how can you convert back and forth between numbers in different bases. It turns out converting a number into base 10 is a relatively simple process, and let's try that here in example 2. So, if possible, convert the following numerals to a base 10 number. And I put this one here first. This is 3, 7, base 5. Notice I'm not saying 37. This is 37 base 5. Is it possible to convert this to a base 10 number? And there's a problem actually with this 37 base 5. Do you see it? The issue is in base 5, you can only use the symbols 0, 1, 2, 3, and 4. And right here, there's a 7. So this number I wrote down is actually meaningless. This means absolutely nothing because of the 7. What I'll do is put a different base 5 number that makes sense down. So here's one. How about 3, 2, base 5? This is okay. 3 and 2 appear on the numbers, the symbols that you're allowed to use on a base 5 list. Now, how do I convert this into its base 10 equivalent? The way we can do that is by using the place values of each number. So here, this 2 is in the 1's place, and this 3 here is in the 5's place. And the reason for that is here, this is the 5 to the 0 place, which is a 1's place. And this 3 is the 5 to the 1st place, which is just 5. Here's how you expand this number out. You take the digit and you multiply it to its place value, which this 3 would get multiplied to 5 to the 1st, or 5. So I'll write that down. This is 3 times 5 to the 1st. To that, you add on the same thing, but for the other place value, which is 2. So that's 2 times 5 to the 0. If you simplify this, this will be a base 10 number. So this is 3 times 5 plus 2 times 1. 3 times 5 is 15. 2 times 1 is 2. And this is 17. And this is base 10. So if you see the symbol 32, but you're talking about base 5, this does not mean the number 32. What this means is we're in a different base, but we're really talking about 17, base 10, the number that we're probably more familiar with. Let's try this again with the number 301 base 4. First, notice that this number makes sense. In base 4, you can only use 0, 1, 2, and 3, and all of these digits are okay in this case. What I'm going to first do is write down the place value for each digit. This 1 is in the 4 to the 0 place, which is 1. This 0 is in the 4 to the 1st place, which is the 4's place. And lastly, this 3 is in the 4 to the power of 2, which is the 16's place. In order to expand this out to a base 10 number, we take the digit and multiply it to its place value. Starting with this 3, that will be 3 times 4 squared. To that, we add 0 times 4 to the 1st. And then the last thing we have is 1 times 4 to the 0. If we simplify this, this will be a base 10 number. So that's 3 times 16, plus 0 times really just 4, and then plus 1 times 1. All right, so 3 times 16 is 48, plus 0 plus 1, this is 49, and that's 49 base 10. So here, in this case, 301 base 4 is the same thing as saying 49, a decimal number. All right, so for this last part of example 2, here we have 1182 base 9. Again, notice that this number makes sense. We're only using digits that go from 0 to 8. There's no 9 or anything further. So to expand this out, I'll put it down here. This is equal to, this 2 is in the 9 to the 0's place, which is just 1. This 8 is in the 9 to the 1st place, which is just 9. This 1 is in the 9 to the power of 2 place, which is 9 times 9, that's 81. And then this last one is into the 9 to the power of 3 place. So 9 times 9 times 9 is 81 times 9. That's 729. I'll carefully expand this out. I'll take each digit and multiply it to its corresponding place value. Starting with this 1, this is 1 times 9 cubed, plus, then it's going to be 1 times 9 squared, plus 8 times 9 to the 1st, plus 2 times 9 to the power of 0. If we simplify this, that's 1 times 729, plus 1 times 81, plus 8 times 9, and that's plus 2 times 1. So that's 729 plus 81 plus 8 times 9 is 72, and then plus 2 times 1 is 2. If we sum all of these together, so that's 729 plus 81 plus 72 plus 2, that's 884. And this is a base 10 number. So here we took numbers in different bases that were different than 10 and converted them into base 10 numbers. Okay, so here in example 3, we're going to do this process backwards. We're going to go from a base 10 numeral to something in a different base, in this case, 5. How do we take 9, or 9 base 10, and switch that to a base 5 numeral? So really we're doing something like 9, which is in base 10, that should somehow be written as something in base 5. And since we're using base 5, you can only use 0, 1, 2, 3, and 4, and that's it. There's a trick that you can do here that makes this kind of nice, in a way where you probably can even figure this out in your head. So we have 9, and 9 is base 10. Can you somehow write this as a sum that uses the number 5? And there is one way to do that. You can say that 9 is the same thing as 5 plus 4. Now, why would this help us write out 9 as a base 5 number? And the reason is because here we have 5 to the power of 1. And that will tell me the digit that's going to be in the 5's place. If we also had 5 to the power of 0, then I know the digit that's going to be in the 1's place. And, it's not written here, but I'll put it here for emphasis. 4 is the same thing as 4 times 1. I could really rewrite 5 plus 4 as 5 to the first plus 4 times 5 to the power of 0. So here, this is the 1's place for base 5, and the digit 4, which is on my list, is sitting right here. This will tell me the digit that goes in the 5's place. It's not written, but I can put for emphasis 1 times 5 to the first. What we've done is we've taken 9 and we've written it in a way so I can see powers of 5. To get your answer from here is very quick. You can just look at the digits that appear in front of the 5's. In this case, the 5 to the 0 and the 5 to the first. Those digits are 1 and 4. So how do you write 9 in base 5? It's 1, 4, base 5. And I'll put that over here. If you want to check that this worked, we could do this process backwards. Can you expand 1, 4, base 5 and get the number 9 back? This is what we were doing in the previous slide, but I think it's worth writing it out. We don't have to do this every time, but it's good to see why this worked. If you have 1, 4, base 5, this place value is the 1's, this place value is the 5's. So you could say, oh, well, this 4 is in the 5 to the 0's place, which is 1, and this 1 is in the 5 to the first place, which is the 5's. To expand it out, you take the digit and multiply it by the base value. So it's going to be 1 times 5 to the first plus 4 times 5 to the power of 0. That is exactly what's written right here. And if you combine all this together, you do in fact get 9, which is a base 10 number. So here's a process that we can use. Essentially, if the number is small enough, you could try to write it as a sum using the corresponding base. Then you can figure out the digits that go in front of all of the powers of 5, and then you simply record the digits to get your answer. Let's try this a couple more times. Okay, so in example 4, let's convert a few base 10 numerals into something that's in base 4 and then also in base 6 just for some extra practice. And since we're using a different base, let's use the same base 10 numeral as in the last example, which is 9. I want to convert, to start with, 9, which is in base 10, into, let's start with 6, something that is in base 6. How would we do this? For base 6, you can use the digits 0 through 5. Our trick was, can we write 9 as a sum using the number 6? So with 9, we can. That is 6 plus 3. Fantastic. But how does that help us actually get to a base 6 number? Well, we want to introduce powers of 6 over here, and we're all set with 6. That's 6 to the first. There's really 3 times 1 over here, which I'll put for emphasis, and 1 is the same thing as 6 to the power of 0. So this is 9 is equal to 6 to the first plus 3 times 6 to the power of 0. There is a 1 that's being multiplied to the 6 to the first, so I'll put it in here for emphasis. 9 is the same thing as 1 times 6 to the first plus 3 times 6 to the power of 0. At this point, we have our answer. It is the digits that appear in front of the powers of 6. So I'll write this out as 9 base 10 is the same thing as 1, 3 base 6. All right, let's try it again, but instead of going to base 6, let's try out base 4. Let's see if this process will work. So we have 9 base 10, and I want to somehow write that as something base 4. Okay, so again, using this trick, I want to write 9 with a sum with 4, and that's going to be 4, I guess 4 plus 5. I think there's going to be an issue here. If we try to follow along with the logic that we used up here, hey, this 4 is great, right? Here we have 4 to the first, and I know it's really 1 times 4 to the first. Unfortunately, we can't just say, oh, well, I'll put a 4 to the 0 here and then gather up the numbers that appear in front of my powers of 4. Why can't we do that? For base 4, you can only use 0, 1, 2, and 3. And here's the digit 5. So unfortunately, we need to try something else. So it didn't quite work out, but let's try again. It is true that 9 is equal to 4 plus 5, but the issue here was the number 5. We can actually break this number down using the base 4. In fact, 5 is 4 plus 1. So this is 4 plus, since 5 is 4 plus 1, I'll put 4 plus 1. Or, said another way, 9 is equal to, well, here I have 2 4s. So you can say that's 2 times 4 plus 1. And this plus 1 at the end, we can say, well, why don't we multiply that by 4 to the power of 0? Expressed in this way, we have our answer. If I take this 2 and this 1, we have that 9 base 10 is 2, 1 base 4. And again, you can check your work on this. You can say, well, did this in fact work? Is 2, 1 base 4 really equal to 9 base 10? If you expand it out, you'd say, well, this is the 1's place, and this is the 4's place. We'll do 2 times 4 to the first, plus 1 times 4 to the 0. And that is exactly the expression that we have right here. 2 times 4 to the first is 8, plus 1 times 4 to the 0 is 1. This is equal to 8 plus 1, and that's in fact 9 base 10. All right, let's try this again just with some different bases. Here I'm going to go back to our number of sheep in a field, which I think we said this was 2 groups of 10 and 1 left over, so 21 base 10 sheep. What would this be as a base 8 numeral? So that is, how would I take 21, which is in base 10, and convert that into something that is in base 8? Using the trick that we talked about, can you somehow write 21 as a sum using 8s? And sure, you could say, well, yeah, that's equal to 8 plus 13. But as we saw in the previous slide, this 13 is going to be an issue. So maybe this is not a great starting point. Maybe we should count by 8s until we can get as close to 21 as possible. So that is, all right, well, I know 21 is equal to, all right, well, you can put an 8, but you can add another 8 because that would take you to 16. But you can't add 8 again because that'll take you to 24, which is too far. So if you use 8 plus 8, that's 16, and the amount that's left over from 21 is 5. Or you could really jump right to 21 is equal to 2 times 8 plus 5. Here the trick being, get as close to 21 using 8 as possible. You can go twice. You can't go 3 times because it's going to be too much. We are now very close to the final answer to expressing 21 as a base 8 number. The only thing that's really missing here is a 1 or an 8 to the 0, but you can simply add that. In fact, you could put a 1 up here for emphasis. I can now use the digit 2 and the digit 5 to represent 21 as a base 8 number. So what's 21 base 10? It is equal to 2, 5 base 8. And we'll try this one more time. That was base 8. What about if we convert to base 7? So that is, we have 21 base 10, but I really want to write that as something base 7. So let's see. How close can you get to 21 if you're counting by sevens? And you could list it out like adding 7 over and over again, or you could even jump down to something like this. I know 21 is 3 times 7. Why don't we just start there? That means you counted by 7 a total of 3 times. In fact, it works perfectly. 3 times 7 is, in fact, 21. How much is left over? Just to be careful, you can say, well, nothing. I don't have to add anything else. And that zeroes in the ones place. So how can I express 21 base 10 as a base 7 numeral? I can use the 3 and the 0. So that would be 3, 0, base 7. So here's 21 base 10 as a base 7 number, and also a base 8 number. Okay, so let's try this one last time here in example 6, where we will convert the base 10 numeral 129 to something that is in base 4. So I'm looking at this as we have 129, which is in base 10, and that should be something in base 4, meaning we're only using 0, 1, 2, and 3 as our digits in the final answer. I think this is going to be kind of a more difficult process only because this number is large. And the reason for this is we might have to use several place values in order to get close enough to 129. I'm going to list out a few of the place values for 4 if we're working in base 4. It starts out simple. You have 4 to the 0, which is 1. 4 to the first, which is just 4. You keep going, get 4 squared, which is 16. 4 cubed, which is 64. If we go one more, 4 to the 4th, that's 256. This is too far. I mean, if you use a digit in this place value, you're going to be larger than this number. But I think we're going to have to go to this place value here in order to reach 129. What this means is if you want to write 129, which is in base 10, as a base 4 number, you're going to have some digit that's in the 4 to the power of 3 place. And then you're going to have some other digit that's in the 4 to the power of 2 place. And this trend will continue. Got to come up with some digit that is in the 4 to the first place, and then some digit that's in the 4 to the power of 0 place. This is a harder problem because in the previous examples, we only had to go here. In this one, we got to go a little bit further. So the question is, how close can you get to 129 by using this largest place value? Well, the biggest digit that you can put here is a 3. Either 3 times 4 to the power of 3 is going to be bigger than 129 or it's going to be smaller than it. And I'm just going to check this on my calculator because it'll take a while to multiply this by hand. So 3 times 4 to the power of 3 is 192. So the question is like, could I put the number 3 here? And the answer is no, because 3 times 4 cubed is 192. That means we went too far. Can I use 2? Could I put a 2 in this spot? Well, 2 times 4 cubed, let me check that. That's 128. That's very close. But here's what we figured out. Some digit has to go here. You can't use 3 because it actually moved us past this number, but you can use 2. In fact, it gets us very close. So I'm going to put a 2 here. So in constructing the base 4 number, I have to have a 2 in the 4 to the power of 3 place. Now the question is, you need a digit here, here, and here. Again, only using numbers that appear on this list. I know one more is going to take us to 129, and that has to be down here in the ones place, which is a 1. We do have to put things in this place value here and here. That must mean we use 0. So how can you write 129, which is in base 10, as a base 4 number? It's going to be these 4 digits with a subscript of 4. That is, we get 2, 0, 0, 1, base 4. So here's how you can convert from a large base 10 number into a smaller base. One final thought for this section: can a base be greater than 10? And the answer to this is yes. You could have base 11, base 12, and so on. And I want to look at base b is equal to 16, which is also referred to as hexadecimal. In this base system, you're using 16 symbols to represent your numbers. The convention is you can still use the digits 0 through 9. That's a total of 10 digits, but you need 6 more. So what do you use? Letters A, B, C, D, E, and finally F. They do represent something numerical. Here A represents 10, B is 11, C is 12, and so on. So you can write numerals using these digits here as well as these letters. So here is an example of something that is in hexadecimal. You could write, let's say, 9E, 7, and F. What are the place values for these digits? It works the same way with base 10, base 2, base 5, whatever. This is going to be, since we're base 16, that's 16 to the 0, which is 1. Here, this is going to be 16 to the power of 1, which is simply just 16. Here, this is 16 squared, which is 256. And lastly, this place value is going to be 16 cubed. And 16 cubed is 4,096. How do we go about expressing this hexadecimal or base 16 number as something in base 10, just so we're a little bit more familiar with it? You expand it out the same exact way that we did with every single other number. The only difference is if you have a letter instead of a digit, you just go to this list and say, oh, well, E represents 14 and F represents 15. So this is going to be the digit 9 times its place value, which is 16 cubed, plus E, which has a value of 14, times its place value, which is 16 squared, plus 7 times 16 to the first, plus F, which has a value of 15, multiplied to its place value, which is 16 to the power of 0. So I'll finish writing this out. This is 9 times 4,096, plus 14 times 256, plus 7 times 16, plus 15 times 1. I'm just going to type all that into my calculator. Okay, and the value I get is a base 10 numeral that is 40,575. So that's base 10, which is actually this number right here. Now, why use a base that is greater than 10? In terms of storing data, larger bases can be nicer to use. Notice that if you go from base 10 to base 2, if you drop down to a smaller base, the number of digits that you have to use is greater. There's going to be more digits over here. Likewise, if you go to a larger base, you're using fewer digits to represent your number. So here you have this base 10 number, 40,575. You could actually store that as 9E7F, and you're using one less place value to do so. So in computing, it might be beneficial to use a larger base just because in terms of storing the value, the numeral, you're using less storage in order to do so.